Let's start with the definition. The number of combinations of R distinct objects from a set of N distinct objects is C of NR, which is equal to P of NR. This is the permutation formula, divided by R factorial, which simplifies to N factorial divided by R factorial times N minus R factorial. And R will be in the range of 0 to N inclusive. Now, some people also write it this way: the C with the NR here, or the C with the NR here, or sometimes even just in parentheses N over R this way. All right. Now, in my last video, I talked about permutations. And remember that I said with permutations, order matters. And in combinations, order doesn't matter. And what I mean by this is that if the objects you choose from the set happen to be 1, 2, and 3, or if you were to choose 3, 2, and 1, in terms of permutations, these are not considered the same thing. They're considered two distinct orderings. So for example, if you had some type of contest, the person who won first, the person who won second, the person who won third would be different here than if we had this right here, right? But if you're talking about combinations, 1, 2, 3 is equal to 3, 2, 1. So if I reach into a bag and just grab 3 things, but I'm pulling them out one at a time, typically we don't care what order I pulled out the 3 things. All we care about is the 3 things. Okay? So let's see where this comes from. Let's look at this example. So let's say I have this. I have the set of possible values A, B, C, and D. And let's say we choose 3 of these at a time. So let's say I happen to choose the A, B, and the C. So I could pull them in this order: A, B, C, A, C, D, or excuse me, B, B, A, C, B, C, A, C, A, B, and C, B, A. If I choose these 3 things, A, B, and C, these are the 3 ways to arrange them. But what if I had A, B, D? A, B, D, A, D, B, B, A, D, B, D, A, D, A, B, D, B, A. I could have A, C, D, A, C, D, A, D, C, C, A, D, C, D, A, D, A, C, and D, C, A. And finally, B, C, and D. B, C, D, B, D, C, C, B, D, C, D, B, D, B, C, and D, C, B. So there's 6 rows, 4 columns. We can see there's 24 different things here. So if I was talking about permutations, it would say P of 4, 3, which would be equal to 4 factorial divided by 4 minus 3 factorial. 4 times factorial is 4, times 3 is 12, times 2 is 24, times 1 is still 24. We have 24. This right here would end up being 1 factorial, which is just 1. And that gives me 24 different things. But we said that if we're talking about combinations, all 6 of the things in this column are the same. These 6 are the same, these 6 are the same, and these 6 are the same, which means I only have 4 combinations of the values in this set if they're chosen 3 at a time. Does the formula support that? Well, we have C 4, 3 is equal to, and we're going to use this over here, so I'll have 4 factorial divided by 3 factorial times 4 minus 3 factorial, And this is 4 times 3 factorial. 3 factorial times 1 factorial. So these cancel out, leaving 4 over 1, which is 4. So what are we doing here? Well, we're dividing the 24 possibilities by the amount of ways we can combine A, B, and C. Because basically this column right here gives us 6 times too many of a count when we're talking about combinations versus permutations. There's 6 permutations here. There's only 1 combination. So that's the reason why we have this over here. You take the number of permutations and divide by how many redundant arrangements there are. There's really 6, right, for each of these. And that's why we divide by the 3 factorial, which is 6, and that gives us the 4. All right. Now, let's look at some more examples. If you're looking at a textbook on combinatorics, it's fairly common to see examples that involve playing cards. That is, how many hands of this or how many hands of that can you get? So let's look at some of those and see where they come from. So let's start with the standard 52 card deck. And how are those arranged? Well, we have 4 suits. So we have diamonds, clubs, spades, and hearts. And the values are ace, 2, 3, ... 10, jack, queen, and king. So these are the suits. So end up being 4 suits. And we have 13 values within a suit. That's what we have here. Ace, like 1, 1, 2, 3, 10, 11, 12, 13. Right? So, how many 5-card hands? Now, in many card games, you're just dealt your 5 cards, and we don't care about the order that you get them, because you don't, depending on the game, of course, but many games, you don't start doing anything until you've gotten all 5 of your cards. So whether you get, say, ace, 2, 3, 4, and 5 of hearts, or you get 5, 2, 3, ace, 4 of hearts, that doesn't make any difference, right? So what does this end up being? Well, it's a combination problem because the ordering doesn't matter. And so this is C of 52, 52 cards chosen 5 at a time, which is the 52 factorial divided by 5 factorial times 52 minus 5 factorial. And this becomes 2,598,960. All right. So there's about 2.5 million different possible hands. All right. So that's one problem. But of course, different hands win different games, right? So what if we have 4 of a kind? This means that we will have all 4 cards from a particular kind, like all the 3s. Okay, so we would have one representative from each of the 4 suits, and then we just have one of the other values. So how do we think about that? So let's look at this. So an example would be this. We have, say, the 3 of hearts, 3 of diamonds, 3 of spades, 3 of clubs, and say the jack of diamonds would be 1 4 of a kind. So 3, 3, 3, 3, and then something else. So value of 4 cards, value of 4 cards of same value Well, we have 13 different possible values, so we're saying pick one of those 13. But in terms of combinatorics, what is that? Well, let's see of 13 choices, choose one at a time. 13 factorial, divided by 1 factorial, divided by 13 minus 1 factorial, which is 13 times 12 factorial, divided by the 1 times 12 factorial. These cancel out, leaving 13. And then what about the last card? Value of other card, or value of fifth card, let's say that. So what are the possibilities? Well, we have 52 cards, and we just used 4 of them for this. So there's 48 possibilities. Okay? And we're going to pick one of those. So we could say this is C of 48. Pick one, which would be the 48. Another way to look at it is choose one of the other 12 values. So other 12 values, receive 12, times one of the 4 cards of that value. So the suit. So if you pick, for example, if we had this example right here, we have the 3s, now we have the other 48 cards. Maybe we picked Jack as one of the 12, and for each of those possible jacks, there's 4 possible suits. So this still don't be 48, but either way you look at it, we could say it's this. If we use the second example, or method, I should say. So there's 624 of those. Let's look at another example. A full house. What this means is 3 of one kind and 2 of another kind. So we might have, 7 of hearts, 7 of spades, 7 of clubs, 5 of diamonds, 5 of hearts. So 3 of these, 2 of these. So we have 3 of a kind. That is, out of the possibilities, we have 13 different possibilities for these. Okay? So we'll say here the value. For example, 7 is one of those 13 values. But now, which 3 of those do we choose from? There's 4 possibilities, right? There's 4 suits. So which 3 cards So out of the 4 possible 7s, which 3 do you choose? Happens to be 4 different arrangements of those, or combinations of those, okay? And this right here is equal to 13. And then for the 2 of the kind, the value, well, it's one of the other 12. And then which 2 cards of that? So we choose of the 4, 2 of the 4, right? So we could have the 5 of diamonds, the 5 of hearts, or the 5 of diamonds and the 5 of spades, or whatever. And so ultimately we end up with this product here. So we'll have C of 13, C of 13 one at a time, times C of 4, choose 3 at a time, times C of 12, choose 1 at a time, times C of 4, choose 2 at a time, and that's equal to 3,744. Okay, that's how many full houses we have. And let's look at something that's going to be a little more tricky here. So about 3 of a kind. What does this mean? Well, it means 3 of one value plus 2 other cards that are not of this value but not equal to each other. Okay, so what do I mean by that? So we have, 7 of hearts, 7 of diamonds, 7 of spades, and I'm going to do something wrong here. So then if I have my 5 of diamonds, 5 of hearts, we call this a full house. So this wouldn't work. But I could have, say, 10 of clubs. So 3 of a kind plus 2 other cards that are not of the same value, and none of these then could be the other 7, because then that'd be 4 of a kind. So how do we work this? Well, the first part's the same as we did before. So the 3 cards is still going to be C of 13, choose 1 for which of the 13 values we want. Which 3 within that is C of 4, 3. So there's 52 of these. But what if we just picked any other 2 cards? We didn't worry about full houses. Okay, so if allow any 2 cards other than, right, remaining card of value above. So what I mean, I'm not allowing, in this case, if I had the 7 of hearts, 7 of diamonds, 7 of spades, I don't allow the 7 of clubs. So what would we have then? Well, we picked 3 cards, but really we have to throw out the 4th card, the other 7 here. Okay? So if we did that, then we would have, C of 52 minus the 3 cards here, minus the remaining 1, taking 2 at a time, which is really C of 52 minus 4, which is 48, taking a 2. Okay? And so this is our 48 factorial divided by 2 factorial times 46 factorial. Now if we do it this way, and this is technically wrong, but I'm working towards something, then what we have here is C of 13, 1, times C of 4, 3, times C of 48, 2, which is equal to 58,656. But the problem with this is it includes the full houses, right? Because 3 of a kind doesn't allow 2 matching cards here, not 2 5s, 2 7s, or whatever. So to get what we actually want then, so 3 of a kinds would be the 58,656 minus the 3744 that we had right here. Which is 54,912. So this is the number of 3 of a kinds. So 58,656 allows all 3 card matches where the only real restriction is that we can't have the other card of these the three valued ones, but we do allow full houses. That would be 58, 656. But if we subtract out the full houses, then we get this, and this is the true answer for 3 of a kind. Now, there's other ways to do this. If you look it up online, they're going to do it this way, typically. They'll say, okay, for the other 2 cards, this top part is still the same. So for the other 2 cards, we have 12 possible values. And so that's C of 12, 2, right? But they're of 2 different suits, okay? So we could have, because what are we doing here? When we say 2 other cards here, we're saying, like, if I picked the 7s here, out of the other 12 possibilities, maybe pick a 5 and maybe pick a 10. So these would be 2 different values. And then for value 1 for the 5s, there's 4 possible suits. So the suit of card 1, choose 1 out of the 4, and then for, say if we had the 10 for the other value, there's 4 possible suits for it. So if you do it this way, then it becomes C of 13, 1 times C of 4, 3. This gives you the 3 cards. And then to get the other 2 cards, it's C of 12, 2 times C of 4, 1 times C of 4, 1. And once again, this will be equal to the 54,912. So there's different ways to think about it. When I think about it, this is the way I thought about it. If you look it up online, this is the way you'll see it probably. But there's different ways. But in each way, we can do it with combinations using the formula I gave you. So there's an introduction to combinations as part of a discussion of combinatorics.